Our next speaker is Melissa Maynard, and she is going to talk about the geotechnical issues that we didn't think there were any geotechnical issues when we got started. Right, Melissa?
Right. Well, that's okay. Everyone's always learning, right? Okay, so I am in the Civil and Environmental Engineering Department at Maine, and my background is on offshore geotechnics and soft soils, so this is a perfect combination of both of those things. So first of all, I just want to give you some background. This project that I'm talking about is funded through the ORPC commercialization project, not the earmarked money that was most of the other projects are funded under. And so when I came to the university, Mick sought me out to be involved with the Tidal Energy project and give my geotechnical and geology expertise. And so the role of geology and geotechnics in tidal energy. So the offshore site investigation group of the Society of Underwater Technology in the UK says it's to demonstrate the feasibility, the suitability, and the relative installation risk of preferred design concepts for foundations and cable routes. The ORPC turbine has both foundations and a cable route. And so when we think about geology and geotechnics, when we do a site investigation, we're looking at the bathymetry or the water depth. We're looking at the meta-ocean conditions. We're concerned with the waves and the current and how that is going to affect any substructure that's going to have to be founded in addition to the turbine. We're also looking at the geophysical surveys and the seafloor setting, what types of sediments we have, what types of layering of sediments, the depth to bedrock, and so on. And then when we finally get out of the geology and the mid-ocean realm, we're looking at the geotechnical parameters, which are what is the compressibility of the settlements? Is your infrastructure going to settle? What is the strength? Is the infrastructure going to be able to withstand the lateral and the vertical loading put on it in the water, and how do we approach the design? As geologists and engineers, we then look at developing a subsurface model, and we also look for hazards. It's not a big deal in Maine, but faulting is certainly a hazard we're concerned with in some offshore regions. We're focused on submarine landslides, we're focused on natural gas, none of which we found in conjunction with this project, which is great. And then we quantify uncertainty and risk. So those are the types of things that we think about as engineers and geologists when we develop infrastructure for tidal energy. Now, when I first came here, I had to become more familiar with the geology of Maine and some of the energy devices themselves. And so I began to look for challenges where we needed to focus some of our research efforts in order to essentially make tidal energy more cost-effective and safe, and to incorporate not only a single turbine, but an array of turbines in a cost-effective manner. And so there's a few challenges, one of which is complex geology. Most of the tidal regions in the U.S. happen to be near shore in geologically complex areas where you don't have a single layer of soil overlaying bedrock. You have variability, and that's based on sedimentary features that are more land-based sedimentary features, particularly in Maine when sea level used to be 60 meters lower than it is now. And so just to illustrate some of the complex geology that we face for the ORPC project this is one of the sub-bottom profiles. So we use a sonic source and then a set of hydrophones which allow us to pick up reflections within the sediment and the sediment layering. And so you can see we're looking for bedrock depth, we're looking for variable thickness, we're looking for geohazards and different layering. And what this profile is showing us down here is we think, just based on the sound profile, that's the bedrock surface. So when you're thinking about having to put out foundations, and those foundations have to be a certain length, there's only some regions that you can put these tidal devices, or you have to modify your foundation type in order to accommodate a shallower sediment thickness. And then this brings us to the challenge of siting not just one turbine, but multiple turbines. And so this image is an example of a North Sea wind farm where they're trying to put these spacings at maybe wind farms at 1 kilometer spacings, and then you see in the black lines these paleo channels that are going to impact some of the locations where you're going to have to put a foundation. And so then that becomes, do I have to have a different foundation design for every single turbine, and that drives up cost? Or do I have to have 1 or 2 foundation designs that I can use across my entire site, which will help to reduce cost of actually manufacturing and having the equipment to install and the actual time to install once we ramp up and get more experience doing the installation. Another challenge, and this one is a little bit dear to my heart, is geotechnical investigation. Now, my background is at the Center for Offshore Foundation Systems at Western Australia, and that's mainly for oil and gas. A lot of the infrastructure that we use for the oil and gas industry is not appropriate for shallow water coastal regions where you can't bring in big ships without having a really large impact, or you need a lot more water depth, or in order to achieve the things that we want to do, which is collecting samples and doing penetration tests to get at engineering parameters of the subsurface. An additional thing that tidal energy provides in terms of a challenge is the fact that we have fast water, we have a very small time frame for slack tide where you can do operations that require a lot of motion and movement, and when you're thinking about having a drill string in 80 feet of water and you have a 6-knot current, there's going to be a lot of energy around the drill string, which is going to impact your ability to collect samples throughout the entire time frame. A second thing, aside from just the tidal influence and the forces that that puts on our site investigation resources to get actual geotechnical data, we have to worry about winter in our region, where bad weather days drive up costs because you can't operate but you still have the equipment mobilized. And so we have to come up with some sort of solution to get the information that we need in a more cheap way, in a robust manner, and that can happen at all times of the year instead of just focusing on certain weather windows. And at the same time, we want to practice engineering safely, economically, and then have the equipment capacity and the availability. One of the challenges that tidal energy faces is availability of equipment. So theoretically, maybe we could use a jack-up barge if we had low flow velocities, but understanding that a lot of these are deployed from either the North Sea or the Gulf of Mexico, and the oil and gas industry has them booked out for years on end, a small developing renewable energy field isn't going to be able to have the same access. And so we need to come up with ways to modify land-based tools or to develop new tools for site characterization. And just to give you some numbers, if you were to do a land-based geotechnical investigation, which might include getting a drill rig, drilling a couple of boreholes, you would spend maybe $1,000 to $5,000 to mobilize the equipment and do the work. If you're an oil and gas drilling entity and you're trying to think about doing a geotechnical site investigation, you're looking at mobilization on the order of $1 to $2 million. You're looking at daily operational costs upwards of $200,000. And then you have to account for water, for bad weather days where you're still paying that price even though you're not getting anything done. So the tidal energy industry can't afford that. The renewable energy industry in general can't afford that because we just don't have the level of investment. And then imagine that that's only for one oil and gas rig with maybe 8 foundations. And then think about an ORPC turbine that has 8 foundations for a single turbine, and then we want to have however many to generate a large enough resource of tidal energy. So we really have to reduce the cost. The next challenge is complex loading, and this has to do with the fact that a lot of what we know about offshore foundations and offshore site investigation comes from the oil and gas industry. And while there's a lot of information on foundation types, best practices, design codes, the way that the oil and gas industry works is most of their infrastructure is loaded in a very different way. If you think about it, they're resisting loads that we have to optimize use of. So for instance, if they're in a tidal area, they want to do everything that they possibly can to mitigate any loads on their structure from the tides. Whereas for the tidal industry, we have to utilize the energy that we get from the tides. And so that creates a completely different engineering loading scheme that now we have to translate these large lateral loads to the foundations, and now we need a different way to design foundations, a different way to analyze the effects of this lateral loading, particularly understanding that these structures are very light when you think about how heavy oil and gas structures are. So they might seem, they're quite heavy, but when it comes to the ratio between the horizontal to the vertical loads, we're operating in a realm now where we have a higher ratio of horizontal to vertical loads than previous design codes have been developed on. So we have to do these foundation investigation studies in order to move the process of developing efficient foundations for the renewable energy and for the tidal energy industry. And so that leads me to the most interesting aspect of my geotechnical research on tidal energy is the foundations themselves. And so I started a feasibility study on the use of a suction caisson, and I'll describe that in a moment, for fixed seabed tidal structures in soft clays. So it turns out that at the ORPC site we have soft clays, very low strengths, and it's fixed to the seabed, meaning it's not a moored structure. And we're using a suction caisson. And a suction caisson, essentially, if you look over here, is just an upside-down soup can that it penetrates under self-weight when you set it on the seafloor, and then you see that little blue arrow that comes up, and you actually suck out the water in the top, which is why it's called a suction caisson. And that operates, and at the end that's sealed, and then that operates as a resistive mechanism, so it provides both lateral capacity because you have a large distance that's penetrated into the soil, and it provides good vertical capacity because it's a sealed system, and you develop water pressures that prevent the caisson from pulling out at low loading. And that's just an example of a suction caisson. The foundations that the ORPC turbine has right now is a pile system, and the disadvantage of using a pile system is that you have to have a hammer. You have to put dynamic energy into getting the piles down to the elevation that you're interested in. The beauty of the suction caisson is once you put it on the seafloor using a crane, you just use a pump to suck out water. You don't have to worry about the permitting aspects and the large equipment that comes along with requirements to drive piles. And so my study is looking at suction caissons, both a numerical modeling study and then a physical modeling study by which we actually develop a small scale model, test it in soil to see what the capacity is. And so we started with one of the original ORPC designs, or rather, we're looking just at one of the trusses, and so you can imagine the turbine is coming in and out of the page, and this is just one section. The research is looking at paired foundations, where we have variable bedrock depth. We're concerned with if we have shallow bedrock, if we have deep bedrock, we want to cover that. We're looking at variable foundation length. If we have shallow bedrock, we need to have a short foundation. If we have deep bedrock, we need a longer one. And we're looking at the spacing between the two foundations. So this gives us some availability to vary the truss geometry so that we can design, so we can come up with design parameters. And essentially, we're looking at the limiting capacity of this system. So how much horizontal load can we apply before we reach some sort of failure? And then it's scenarios like this that help inform us how to best design this type of foundation system for an actual turbine. So in addition to looking at the actual geometry of the foundation, we have to have some idea about what the seafloor soils are going to do or how they're going to perform when we install the foundation and then we actually load the foundation and the structure. And so here are the actual data that were collected from the ORPC site where the turbine is now, where you have in the leftmost plot you have various measurements of the undrained shear strength. So the shear strength when it's loaded in a very quick fashion. And then we essentially developed a profile of best guess undrained shear strength values to set as this is the strength that the soil has and this is our limiting factor. If the soil needs to be stronger, we have to design a different type of foundation for instance. And so these are results of some numerical, two-dimensional numerical models looking at different, you'll see D over D. So D is the diameter of the foundation. The small d is the diameter of the foundation. The big D is the depth of the foundation. And you can see that if you just have foundations sitting on the surface, we get a sliding mechanism, and there's this very small area shown in blue right here where you see a change in stress, or this is showing essentially deformation. So we're getting deformation. And then as you increase the foundation length, you start to change the mechanism of failure, where you get a horizontal wedge up in the upper right-hand corner, and then you start to see more of an interaction between the two foundation types when you increase the depth of the foundation. So you're transferring a lot more strain deeper down, and you're getting a lot more capacity deeper down because your zone of influence is much higher. And so looking at these, we end up with essentially a failure envelope. And so for two cases, one where we're just considering the aspect ratio of the footings, and the second is we're considering the end bearing, which is, those are just two different technical ways to analyze your foundation. We get this failure envelope here, where over here at low depth to foundation, or foundation width to depth ratios, we're essentially controlled by sliding, and then once you move D over B greater than 2, essentially you're controlled by the scoop mechanism, where you get a constant horizontal resistance, and then you only have to worry about vertical loading in the moment that you apply to the soil. So essentially what this research is doing is developing these new design tools and criteria to look at, can we develop a new method for analyzing these different foundation types in a simple way that hasn't actually ever been done before. So it's quite interesting and hopefully useful to ORPC for their future developments. Now, just to segue away from foundations for geotech, the other aspect of research that we're considering is how can we improve our site investigation tools. And so, for instance, I've been working with a number of colleagues on projects ranging from getting small-scale cone penetration devices that measure resistance upon penetration into the seafloor, and that resistance we can then correlate to some strength value. And that can be deployed from a small vessel. We're talking on the order of 20 feet maybe, 40 feet, and then can investigate the soil to a depth of 10 meters. It's not the full depth that we want to get at, but it's a good start. And then I'm working with Ryan Beaumont on another DOE proposal we submitted to develop a new type of tool that we can deploy off small vessels again in Maine. And then the University of Maine was actually recently awarded a remotely operated vehicle, so we can actually look at what types of sediments are on the seafloor, and that can give us a better idea about the types of things that we're going to encounter or have to deal with for the design. And then the last thing is I spent a summer, this past summer, working with the Navy on their renewable energy plan and also some offshore geotechnics. And so now I'm starting to look at the use of electrical resistivity as opposed to just acoustics to get sediment characteristics, to get porosity, to get, and then correlate that to shear strength data so that we can get a lot more information using remote sensing before we actually have to put our money where our mouth is to get some tools on the seafloor to collect samples or to do penetration tests. So we can hopefully streamline the process and reduce cost so that for every single foundation location we have to investigate, it's a net smaller cost so that we can have multiple turbines and be cost effective in the same way that, and hopefully cost less than traditional energies cost. And that's all that I have. Yes?
I'd like to say I'm here. I represent a company called SMD out of the UK, and that's significant because they have a marine renewables division. They are an equipment manufacturer, ROV, subsea tractors, and that sort of stuff. But their mission, their strategy is to reduce the cost of tidal system installations. In Two of the things they've developed now is a subsea drill rig that will run on the bottom, drill boreholes, set pilings, all undersea. The second thing they have is a dynamic positioning system that allows the cranes, if you're lowering the system, to work into higher flow velocity and reduce the requirements for divers.
Right.
Which allows all collectively to work in more harsh environments, longer on station time per increment, but much shorter on station time
Right.
collectively.
Right.
And that's what they're doing right now.
Yeah, and I think there's a lot of work going into that, and a lot of what they're doing the same thing for deep water oil and gas investigations, and just transferring the deep water to the shallow water, which it sounds like your company is doing, is going to be a huge step in the right direction.
Yeah, and they can work in the deep water too. I mean, there's really no limit.
Yeah, thank you.
And the next speaker will be Tom Lokos, who's worked on axial flow turbines. Those two designs, the cross-flow turbine is like the ORPC style turbine, where the flow comes across the stream and it looks like an egg beater type of a style. The axial flow turbine is more like your traditional wind turbine, and those represent kind of the standard designs that a lot of the tidal turbine companies throughout the world are making. Our goal here was just to make good models of those so that we could study them, models that had respectable performance compared to what people are producing. One of the issues is in the industry, nobody's willing to really give their data out on how good it performs. So we wanted to provide a baseline. How can you compare System A to System B when you can't get any data? So I think these students have been working for years on getting us to the point where we can comfortably say we can be at the state of the art on turbine design. I think they've done it, and I think they'll show you the results.
Good afternoon. So I'm going to be presenting work that has done by other persons too, Jeff Debris, Matt Cameron, Colleen Swanger. And the first thing that I'm going to present is overview of the concepts. This is the rotor that we have been using at Maine. So the tip speed ratio, the first thing is how fast the blade is rotating with respect to the inflow. So it will be doing this. The second one is the solidity, and is how much of the circumference is being covered by a blade. So there you can see. Also, what is the difference between a cross-flow turbine and an axial flow turbine? The cross-flow turbine, as Rich has pointed out, rotates perpendicular to the inflow, this way. One of the advantages of this turbine is that it can rotate no matter if it's a flood, if the flow is coming this way, or if it's coming this way. It will rotate, so it's less sparks. The other advantage of this turbine is that it rotates at a lower tip-speed ratio. That, in the case of animals, in case of a mechanical strike, the potential of a damage, we expect it to be lower. The other advantage is in rivers, this can cover more area than an actual flow. So the dimensions of our tow tank, they're 100 feet, 8 feet wide, and the depth is 43 inches. The turbine is 30 inches wide, and the radius is 13 inches. I'm going to put a small video. So you can see where it is. So in order for us to be able to characterize this turbine, we needed to have different inputs, which we have the carrier speed, the test distance to get enough wake in order for us to have near steady state behavior. And we measure time, the carrier speed, the turbine position, the turbine torque, the turbine thrust. And we produce the power coefficient, thrust coefficient, torque, and the angle. One of our advantages of our system is that we can control the speed of the turbine, unlike other systems that are there. The first stage that we did is test different blade families. And what I'm referring blade families is that these blades were designed with different criteria. The first one is a NACA 63018 that was first used in war airplanes. And we tested 3 different configurations of this one. The first 2 are different. We produce different type of manufacturing. One by 3D prototyping, the other one with a carbon fiber, and we saw that the deflection was nearly the same one. The second one, the fourth one will be a NACA 0018, and then a Camber one, the NACA 4418, a high lift low drag LMV 109, and then also we tested an S0809 that is an N-rail design blade. After seeing this, we chose the NACA 63018 family and the 0018 family for our further study. So our second stage was looking at the different variables, the number of blades, the camber. You see that this will be the direct camber, and I will be referring to this one as a reverse camber. The toe angle that we can change in our. So we have a line tangential to the turbine, the radius of the turbine. We can change the angle of this, and we can change it. We change it here. This will be this angle. Then the Reynolds number is, we can change it with a different inflow of the velocity and with different chords of the blades. And the chord to radius ratio, the different size of the chord. So what will be the number of blades effect? One would expect if I put more blades into the turbine, I will extract more power. But what happened is that we were less efficient. And this is less may be better. We don't, at the range that we are testing, that's what we have seen, that 2 blades perform much better. The second one is the camber and the toe angle together, and see what were the effects of this one. So the more red is better, as you can see there. So we tested a regular blade, a camber blade, and then the reverse camber blade. And as we can see, I'm going to point it out. There's an optimal toe angle that we get the maximum efficiency. It's around 5. And that is a camber associated to this that we get the maximum. In this case, it was no camber and at 5 degrees. So there may be an optimal configuration that we can get the maximum efficiency. Then we tested the Reynolds number effect within a range, and we saw that there was no really any variation. It's 0.8 meters per second and 1.2 meters per second. Also, we tested 0.6, and there was no apparent performance difference with this change of inflow. So this turbine was didn't show any performance difference. So the next part of our project is producing a model. And why we do this? Because testing is expensive. And I put here the molds in order for us to produce the different blades. The molds are expensive, and we need the carbon fiber and a lot of, just to have a different blades. And testing can be time consuming. Some of the graphs that you've seen have taken weeks to get. And then, how can we translate this test to a prototype? And also, it gives us a better insight of the physics of the problem. So there are different type of models out there, and ones that have been used extensively is the Navier-Stokes, that it solves some fluids equations with turbulence models, and there's many softwares like Fluent, CFX that perform this. The other ones are based on potential flow methods, and that they solve the potential flow in the water. And some of them, they're very suitable because they give us faster solutions to be used in optimizers. So we chose the free vortex method lifting line, and this gives us an advantage because it gives us a simplified representation of a blade just by a point. It gives us the forces, the lift, and the drag. And it calculates a simplified velocity field around the blade with a circulation. Also, we can calculate a simplified velocity field around the blade with time, so we shed vorticity, and we can know what is happening at different time steps. So, in order to represent the physics on the model, one of the main effects that we cover is the dynamic stall. What that means is that we have a blade, and we change the angle of attack, reduce pitch angle, and this will give us a different lift and a different drag. And it has kind of this behavior, this hysteresis that it changes. And it's different within how fast we do it. So if we do it really slow, it will have smaller behavior. Then the virtual camber and the virtual angle of incidence, the flow around the blade is not uniform. It comes from different directions. And then, so normally the tables are done that we have a uniform flow. So we need to account for this. So we change this flow that we have for a camber foil with an angle of incidence, a uniform flow. And the other one is this. These turbines have a cyclic Reynolds number variation. That means that when the flow is going against the blade, we see a higher flow. It's like two cars going against each other. That when the flow is going, the blade is going with the flow, it sees a lower flow. And this gives us, like I explained, a different Reynolds number. So what we decided to do is have a blade representation, and this is because we can have with formulas different cases of what is the blade subject to. And our model is based on separation point, which means that the flow is going to separate from the blade. And we can calculate the lift and drag. So we can produce different approximations for different Reynolds number and from different camber conditions. So the blade, the blade forces can be approximated for multiple conditions of camber, Reynolds number. And so there's no need for tables or interpolations in our model. So the experiments, I'm going to show some results for what happens if we consider an effect like dynamic stall. You see that our predictions are off from our experiments than if we consider the dynamic stall. And also because we have a tow time, we have to account for the effects of having a constricted flow over the tow time. So we can see that we have a better approximation. This is with the efficiency, and now we also consider with the torque. So here I put the positions of the blade, and you can see that without dynamic stall it's really off, and if we consider the dynamic stall, we get a better approximations. And one of the things is that you can see is the blades are like, if you make an analogy with the engine, is you can have the piston that you have force here per each blade. So these are the two blades. here are more results at different angles, and we have pretty good results. So the future work of this is that we need to represent better what is happening with the blade, the velocity field around the blade, like we said that we had simplified. If you see here with the wake, and this red dot will be our blade, it's crossing the wake more times and influencing the velocity and the position of the blade. So what we do is that we represent this blade with a vortex distribution that it gives us a better approximation of the velocity field around the blade, and we superimpose it. So conclusions of my work are that the number of blades may be a more important factor than solidity. That there may be an optimal configuration of the camber and the toe angle that give us a better performance and give us a better, more competitive turbine with respect to axial flows turbines. The dynamic style-based model on reduced pitch rates gives reasonable approximations, and that is one of the things that we've done differently than other models. And one of the things that not only of the optimal configuration of the blade, what we have done is that if you have an optimal configuration, you need to know the forces on the blade in order not to lose lift. We started with a wooden blade, and this will take the force, but it will deflect a lot, and we will lose lift because of this deflection. So this is not only a problem about the loss of a blade, but a deflection one. So what we did is design a carbon fiber blade. We have information and tools for design a better turbine. We have not only tested a 44 NACA 00 series, NACA 4 series, but also a 63018 turbine, and we have the data with the maps of different toe angles and cambers. And we have had a better insight of what is happening with the physics of the problem. I want to thank very much for your attention, and the undergrad students, Thomas McKay, Nate Walker, James Trescott, and especially Jarlath McKenty for all his help, with all the technical help. Thank you.
Well, thank you everyone for coming today. As Mick mentioned, my name's Tom Lokos. I just recently finished a master's degree in mechanical engineering at the University of Maine. And my thesis was on the testing of a ducted axial flow tidal turbine. So I'll talk about that today. The objectives of that research were to provide ducted hydrokinetic axial flow turbine performance data. There's currently no published data that's directly relevant. There are some ducted turbines out there, so somebody has it, but they haven't released it. That data is very important for validating numerical codes for turbine design. And you can see here a picture of the ducted turbine in the University of Maine's tow tank. That turbine is 0.25 meters in diameter. The tow tank is roughly 30 meters long, 2.4 meters wide, and a meter deep. So I started with a free tip turbine to verify the design and the testing methods. This is a known case, so it provides a good benchmark to compare the design and the testing methods with. And then I continued on with a ducted turbine. OpenProp was used as a design tool for this work. It's an open source MATLAB code. It's a programming language. It handles propellers and axial flow turbines. The code optimizes the rotor and outputs a rotor geometry text file that's then imported into a computer program such as SolidWorks for 3D printing. Now, the ducted case and open prop is still very much in development, so that's definitely ongoing work. So why use a duct at all? You can see a set of ducts being fitted to a tugboat here. Essentially, turbines are propellers working in reverse. They simply absorb power out of the water rather than supplying it. For low-speed applications, such as a fish boat or a tugboat, typically you see 20 to 30% efficiency increases from ducts. It's reasonable to think that you'll see something in that range for turbines as well. So how does the duct actually help? You can see a kind of a schematic drawing of a ducted turbine here with the duct section up on the top. Basically, the duct helps by increasing the fluid velocity and the mass flow rate that the rotor, the actual blades, sees. This is achieved because the duct creates a low pressure region downstream of the turbine. You can see the flow here moving from left to right. And a low pressure region increases the fluid velocity. So the rotor sees this and increases power output. So as I mentioned, OpenProp doesn't fully design the duct at this point, but it provides us with some important geometry for the duct, such as the lift coefficient and the inflow angle that the duct sees. From those parameters, the duct profile can be selected and set to the correct angle. NACA 4412 was used for this research. Now you can see SolidWorks renderings here of the free tip and ducted turbines. And on to some results. There are pictures of the free tip and the ducted turbine set up on the test platform, ready for testing in the University's tow tank. Just a little bit about the test platform that was developed for this. It's instrumented pretty heavily to record a number of different parameters. The only ones that are really going to be talked about today involve the torque and the turbine velocity. There's an encoder back here to measure the turbine rate, velocity rate, and a load cell to measure torque. A couple definitions to go through. Power coefficient, which Raul touched on, is really just a non-dimensional way of expressing the power output. It's very similar to efficiency. And the tip speed ratio, once again, it's a non-dimensional way of expressing the speed of the tip of the turbine. It's non-dimensionalized by the inflow velocity. So the results of the free tip testing, you can see the solid or dotted lines here are open prop predictions at two different drag coefficients. The individual data markers are experimental data at a variety of test conditions, specifically a variety of Reynolds numbers. And you can see that the experimental results show pretty decent agreement with OpenProp, and it's also very consistent with other published experimental data. We're able to achieve power coefficient about 0.45, which is the same as OpenProp, although you can see it is shifted a little bit to the left here. It's a slightly lower tip speed ratio than predicted. Now the ducted turbine didn't perform as well as we'd hoped for. You can see once again the two open prop curves at two different drag coefficients with experimental data in the individual markers. The most we're able to achieve out of the ducted turbine was a power coefficient about 0.4, just a little over 0.4, which is definitely not as high as open prop. Now, I also tested the rotor intended for the ducted turbine without the duct in place. The two rotor designs are different for the free tip and the ducted turbines. So to make sure I was comparing apples with apples, I just took the duct off and tested that rotor. And you can see the light blue and the purple marks up on the top are the no duct case. And that case is overall slightly higher than with the duct. So for this turbine, the duct was actually detrimental. So the duct isn't helping, but why not? Well, possible causes are boundary layer separation at the duct, incorrect inflow angle that's given from open prop, could be an incorrect assumption made about the duct drag coefficient that's entered into the code, and this would lead to incorrect velocity, inflow angles, and duct lift coefficient. Just for example, if I use a computer program to predict the drag coefficient for the duct, that program predicts the drag coefficient at about 0.012. This is opposed to 0.02, which is used in the code, open prop. And this changes the required lift coefficient of the duct from 0.5 to 0.2. It changes the inflow angle from -1 degrees to 0 degrees, which changes the duct design. You can see the schematic here. This is a profile of the duct fluid velocity moving from left to right. Beta I is the inflow angle here. And the lift force of the duct acts perpendicular to the local velocity, V star. Now, if we change that inflow angle to 0 degrees, you end up with a lift force acting perpendicular to the free stream flow. So you essentially have no recognized lift force that's contributing to the duct in a useful direction. So you end up with only drag force. So the duct doesn't help at all. So conclusions, the free tip turbine performed pretty well, very consistent with predictions and previous experimental data. We're able to receive a power coefficient about 0.45. The ducted turbine did not perform as we predicted. It didn't produce the required lift force, and that led to underperformance of the turbine. Now, this is a great example of the challenges that are associated with duct turbine design, and it's definitely an area of ongoing research. I'd like to thank Raul, Brennan Epps from MIT, who helped me a lot with this, one of the code developers, and the undergraduates, and of course the Department of Energy for funding. Anyone have any questions?